Hi everyone, welcome back. Hope you all enjoyed lunch and possibly seeing lots of cute animals in the zoo. This is our second industry session. We've got 4 more talks from some very exciting companies for this afternoon. And the first of these is Oxford Quantum Circuits. We've got Andy Patterson come to talk to us about them. He's one of their first quantum engineers, one of the first people they employed. Yeah, hand over to Andy. Thanks very much.
Hi, thanks for the introduction. It's really great to be here at a careers fair, talking to you guys, because as you can see, Oxford Quantum Circuits, we are building the UK's most advanced quantum computer, and to do that, we need great people, and we need a lot more of them. So, yeah, good to be here. At OQC, as was just said, I'm a quantum engineer. By a show of hands, who actually knows what a quantum engineer is? Oh, there are a few. So you notice I didn't put my hand up. Yeah, so my idea of what a quantum engineer is I'm a physicist. I did my PhD in the research group that the company was spun out of. That finished a couple of years ago. And I guess my kind of itch is to build something useful soon. I also really love research and scientific challenges, and it's great when they come up along the way. But I think, as was discussed earlier a bit, we're really focused now on trying to build something useful and bring in customers and users. So why should we be excited about quantum computing? Why do we want to build a quantum computer? I think I'm maybe preaching to the choir a bit already, in that everyone is excited about quantum computing in this room already, maybe. But there's a lot of range of applications listed up here. Probably some of the most exciting near-term ones are the ones involving the material science, material simulation, pharmaceutical drug discovery. Those are the things I hear a lot when I'm talking to our friends and colleagues in the quantum software companies and universities that we're collaborating with. So why do we want to do it from a commercial perspective? Well, there's a huge market opportunity. The worldwide quantum computing market is forecast to be in excess of 10 billion, presumably US dollars, by 2024. And so there's a real chance to make a lot of money out of this as well, which is always good. So, we're in a competitive landscape. Again, as was mentioned earlier, there are lots of different physical systems that you can use to try and build a quantum computer. I'm not going to go through the pros and cons of them all. I would say that I don't think there's like one winner here. It's quite likely that different hardware is suited to different tasks in the end. But at OQC, what we're working on is superconducting circuits. Probably the key reason why we think superconducting circuits are the best way forward to a near-term useful processor is its high engineerability. It's also been shown, I think Ophelia had in her talk earlier, to be rapidly progressing. Sort of in the last 10-20 years, you can plot a line through the quantum computing power available on superconducting circuit systems, and you can see it's starting to reach the ion trap level, and maybe even the potential to overtake it. We're also, excited by the fact that our biggest competitors, such as IBM and Google and Rigetti listed here, also really believe in this approach. But what makes us different? So, at OQC, we are focused on a patented design for the architecture of the actual quantum hardware itself. So what you can see on the diagram on the left here is kind of a cartoon of what a single qubit looks like on one of our chips. You can see it's quite simple. Simplicity is a big deal in designing these systems for a lot of reasons. One is that it's faster and cheaper to fabricate. I think as well as being fast and cheap, it's actually kind of possible to fabricate, which is You can phone. As you're scaling these things up, they become, if they're really tricky at the small scale, and then you're thinking of moving to hundreds or thousands of qubits in the future, you're starting from a really hard place. We've really tried to start from the simplest starting point we can. We've also, from the outset, tried to think about scalability. So you can only see a single qubit here, but what you can see is that we actually put a qubit's kind of a coaxial shape. It sits on the top surface of a chip, sapphire chip, and we bring in a coaxial cable that sits kind of maybe 100, 200 microns above the surface of the chip, and that's how we control it. There's a resonator on the other side. This couples to the qubit. We use our resonator, that's the green circle here, to read out the state of the qubit, and there's a microwave line beneath to allow us to do that. So because of that kind of 1D design, we now have 2 other dimensions to play with. So you can imagine how you can scale this thing up into a grid of qubits of different connectivities quite easily. The flexibility that we mention here is kind of the key reason why I believe in this technology more than anything. It's what makes it exciting, because there's a lot of different ways to play with this kind of architecture in the lab. So for instance, there's a lot of real estate on that chip, and you can put 2 qubits next to each other, and now you can put different things in between to maybe implement some 2 qubit gates, or to try and improve crosstalk, or all these different things. And this is like a really good platform for that kind of innovation. In addition to that, we're looking at, this really is, it's a contactless architecture. So if you look at some other chips from around the world, you'll see a lot of cables kind of coming in and navigating the chip and trying to get to the qubits, and they're bonded from the outside. Whereas our little chips, I've got one in my bag, I can show you guys later, you can kind of just pop them in, pop them out, test another one. It's very quick. So to give you an idea of the company's kind of progress, where we came from, we were founded in June 2017, and I can't remember when I think I started working in July that year, the next year. Yeah, and so you can see kind of some of the key achievements along the way here. Different kinds of qubit numbers, fidelities, patents I think were mentioned earlier. So this is kind of a key part of working in a company as opposed to in academia, to kind of protect the value of what you're working on. So we have a patent on that kind of core Coaxmon architecture that I showed you earlier. Yeah, and we continue to, as we work on different areas of the stack, still kind of consider that at each point is what we're doing something that's patentable, and should we go ahead with that. The last few things listed here are wave scale fabrication. So within a university context, you can get away with building one chip at a time, testing out new ideas, and you're not too worried always about the robustness of the process, how repeatable it is, and whether you can scale it up. So a key part of OQC's work, as opposed to the university groups, has been ensuring we have a robust process for the fabrication. We've been leveraging different facilities around the UK in order to be able to do that, and making sure that we can take these ideas and really reproducibly build bigger and bigger circuits, modular circuits, out of these ideas. So there's a lot to do in building a quantum computer. OQC certainly can't do all of it. We're not a full stack company. There's some different parts of the stack listed here. This is really a complete review, and I think people have different ideas about what's in each of these areas. But so we always have our end user at the start of this thing, and we really have to always be considering them when we're working on something, is what we're doing actually going to have an impact on a user soon? And then between them and a quantum algorithm is some sort of application interface. This kind of together, an algorithm and an interface allow a user to build a program for a quantum computer. And this is not something OQC works on right now. It's something we work with collaborators like Riverlane and CQC. Some of them are listed here to do this part. Then we have a compiler layer. This isn't a quantum software compiler layer. This is a much more low-level system. That's how I actually spend a lot of my time working on at the moment within the company. Been doing that for maybe around a year now. And this translates the quantum instructions into instructions that are kind of physically realizable on a quantum device. So something that's creating electronic signals that are actually being sent to the chip. So from there on, we have this control software, control hardware, and these are things that we're also working with other partners on, but we have some amount of internal development ourselves. And then the quantum device itself is something that right now we're working on as kind of our core component. Alongside that, there's also tools for building these devices. So being able to rapidly iterate and simulate ideas or optimize device designs. There's like a huge tool chain in the standard kind of electronics engineering industry for doing things like this. And that's something that really needs to be it's starting to be worked on kind of across the world for superconducting circuits, but getting that to a point where it can really accelerate our R&D cycle is also something we work on. So I think the key kind of reason I work at OQC is the team, and the reason why I wanted to work in industry as opposed to academia is the variety of skill sets that you get to work with and mingle with and talk to and learn from and also teach during your day. So we have not just physicists, but we have commercial advisors, we have communication specialists, people with backgrounds in kind of hardware, technology, strategy, development planning, so not specific to quantum, but for kind of military or other applications as well. We have people working for us that have run large fabrication facilities, so nanofabrication of our devices is obviously something that's really important to us, and bringing all of this experience together and working together, for me it's great because you learn a lot, and for the team it's obviously great because we can accelerate what we're doing. I, during my PhD, worked a lot on the control systems for these devices. So the fast electronics hardware that's in communication with the quantum device itself, so it's the control hardware that sits in this stack. For enabling like near-term applications, this area of the processor is really important because a lot of near-term applications that they're trying to use the quantum device for kind of just the bit of the quantum algorithm that's most suited to quantum computing. So what we often end up with is algorithms like VQE, for example, where we're running some small part of the program on the quantum device, and then we want to quickly extract that result, react to it, and then continue on with the program. So integration of all of these technologies is a key component here. And so being able to work now with electronics engineers who specialise in that kind of low latency electronics design, and software engineers as well, has been a really great experience, and also I feel like it's enabled us to make good progress. So we're hiring really rapidly at the moment. We would love to hear from anyone. There's like a lot of talk earlier about should you do a PhD, should you go straight into industry. I think if I could just give my take on that, I think you should just do what you find interesting, really. Look at the PhD positions you could take, look at the jobs you could take the ones that you think you would find the most interesting and the ones where you think you'll learn the most. And if you do that, whatever happens, after a few years you're going to have new skills, reusable skills hopefully, maybe not just in the quantum computing space. And you're also going to have enjoyed yourself along the way because it was interesting. And to be honest, like that's what we look for. Your cover letter in an application to a company like ours is like it's more important than the CV. Certainly showing interest and showing the skills that you developed along the way because of that interest is the best thing for us. Working in a startup is like really hard work, and yeah, you do like 3 people's jobs simultaneously, as someone said earlier. And it has really good positives because you learn a lot really quick and you get to do stuff that you're not necessarily qualified to do, and that's the best way to get experience. But yeah, it can be hard work as well, so motivation is the key thing. Yeah, I think that's everything I had to say. So, thanks.
Do you have any questions? Yeah. Sorry.
Do you also have a need for theorists or experimental physicists only?
So definitely not experimental physicists only. Theoretical physics, yes. Obviously there has to be, so for example, simulating noisy devices isn't easy to do realistically. So that's an area where a lot of theorists work right now. Yeah, that would be a really useful skill for software we're currently working on.
Any other questions? Oh, yeah.
So you currently seem quite convinced by your approach to quantum computing. Would you describe what the biggest hurdle is at the moment, technically, for scaling up?
For us specifically, or for people in general? Yeah. So we didn't get into much of like the technology in this, but scaling a system like this is more than just scaling the geometry, obviously. So one thing that you want to make sure you're doing is scaling something usefully, right? So the quality of the individual operations is like a really key component in that decision, essentially. One of the reasons why kind of this technology excites me personally is we can decouple those things. So we can work on these kind of core components of quality, like coherence time of the qubit, fidelities of the operations, changing ways we do 2-qubit gates, which I'm shown here. Those kind of innovations are still necessary. We're nowhere near a point where we can just copy and paste this system to 1,000 qubits. We can copy and paste it away. But yeah, so being able to work on those things without having to necessarily worry about the scaling, I think is a good thing about this. But there are many individual things to improve.